characteristics. As you go towards the end of the semesters, that is 9 and 10, you will see a extreme drop. And suddenly week 12, all of that. Okay. Right. I understand that students are busy with design project, final year project. Yeah. Very stressful for the students. Right. But in a way, as I said, up to today's class, it's fine. If you don't come to the lecture, it's fine because books are there, it's easy. But from next Friday onwards, I think please tell your friends not to cut the class. They should come. Then it's easy. Their life is easier. There is 25 marks gone. Okay. Right. So I have been discussing upon the micro manufacturing techniques. So micro manufacturing techniques is a combination of micro fabrication techniques. Okay? Yeah, ready? So the first technique was bulk micro machining. So in a bulk micro machining, if I want to make a cantilever beam, if I start with a silicon substrate, I have to mask the substrate in such a way that I etch out this region. Okay, so I etch out majority of the region and retain the remaining in a shape of a cantilever beam. In this case, this figure will appear like this. So this becomes a cantilever beam where this edge is fixed, means up to this is fixed, and this is the free edge. So bulk micro machining starts with a complete wafer, and what we do is we etch out the unwanted regions. So we have an unwanted region, removal of unwanted regions through etching. So what do you comment about this technique? Is it a good technique? Give me 1 point for the advantage and 1 point for the disadvantage. What is the advantage? Advantage is simplicity, easy procedure. That means you don't have many process steps. It's probably just use certain mask. I guess some of you have already gone through the laboratory exercises now. So you mask it with the photoresist, then do the etching. Okay. The disadvantage is a lot of resources is wasted, right? Means you remove, it's very unwanted. There is a lot of resources lost by bulk micro machining. So what people have come up with, the next one is the surface micro machining. Surface micro machining is building step by step. So here we don't waste the materials, but rather it's addition of layer after layer. Let's say I want to make a cantilever beam of this shape. So there is a silicon substrate, and above which, say I want to make a cantilever beam of this shape. So let's say this. So this edge is fixed here on the substrate, and there is a free edge. So this material, say this is a polysilicon. So polysilicon is actually a kind of, again, a silicon which can be produced using CVD process, and it is can be deposited on another material. Okay. It's again crystalline structure of a silicon substrate. If this is the one I want to achieve, then how can surface micro machining steps could be? So etching was bulk micro machining, that is removal of materials, so it's wasted. So surface micro machining is creating 3D structures by adding materials on one top of the other. So it involves, again, here also some etching could be there, and also there could be some deposition as well. The thing is, it requires multiple masks and requires a sacrificial layer to create cavities. So I think again I'm coming back to the same analogies. If you remember, I mean the beach example what I used to give. So if you want to make a small igloo type of thing in the sand, you keep your hand and then you fill the sand and you remove the sand. So you make the shape of an igloo or a house type of a sand castle or something like that. So in that case, the hand which you used as was the sacrificial layer that you just later on you remove to get the shape. Okay, so probably such a sacrificial layers are required in building this two-surface micromachine. So if we start with how to make these steps, so the process starts with so they start with the constraint base. They take the silicon wafer as a first step. And on that, they quote here in this picture. It says polysilicate glass. Okay, it's again this is a sacrificial area, but for simplicity, I can say another alternative, which I have already mentioned, would be a silicon dioxide. So silicon dioxide is also a sacrificial layer. So what they might have done, they take the silicon, the wafer, and then they have sent inside the oxidation procedure. So what happened after a few minutes of time, there is top layer of the silicon wafer becomes silicon dioxide. So now it is a combination of silicon and silicon dioxide. The next step what they are trying to do, so the first step is oxidation. Now the second step is to do a photolithography to achieve this step. So what we will do next one is we use the same silicon over which we have the silicon dioxide layer, above which we should now have to make a photoresist coating. Photoresist. Then what we should do, we should take a mask that contains like this. So there is a mask which has which is opaque everywhere, and there is a small opening here. So what will happen is when we do the UV lithography, this region in this photoresist gets dissolved. It will get dissolved, and when you develop this exactly like what we are doing in the lab, you will end up with the photoresist. Silicon dioxide is there at the bottom. You have the photoresist, this guy, something like this. Okay. Then if I do an etching of silicon dioxide, I will end up with the silicon dioxide. If I do an etching of this, so this is development of the photoresist. Okay, I cannot animate everything here. Just I will, as I speak, you please take a note of it. So when I do the development, the photoresist ends up like this. Thereafter, I do an etching of silicon dioxide. After I do an etching of silicon dioxide, that means these regions are protected. So this region, I will dissolve the silicon dioxide here. So it becomes. So I make a cavity of. So there is a space, and then later on, say I remove the photoresist also. So finally, I will end up with. After the etching and development of the silicon dioxide, we will end up with the silicon substrate with the silicon dioxide of this shape. Yeah. So above which then what the next step they are doing is on this, the next step is they now deposit polysilicon using the CVD process. Deposit polysilicon using CVD process. Now again we have to have certain mask to protect maybe certain regions where we don't want to have the polysilicon. So now the polysilicon will be deposited everywhere, something like this. Okay. So do you understand? So what happens is this layer we have the silicon dioxide, above which we are going to deposit the polysilicon, and then remove the silicon dioxide. So when you remove the silicon dioxide, the polysilicon stays like a cantilever beam on the top. So if you see here, the wafer is not wasted. Rather, there was some lithography steps was used and some deposition steps were there to achieve the cantilever beam. So this we call it as surface micromachining process. Okay. Now it is so easy to draw some drawings and say in some steps, but it's quite tedious to do. Even maybe in the lab we are just doing single layer mask. That means in the lab we just keep the mask, we just expose it. We don't worry about the next layers. Okay, but this involves at least 2 mask layers. So there is an alignment is there between these 2 and this. And also the oxidation and the CVD process, they happens at a very high temperatures. So we do not know what all things, other things will go through. So there are several problems also with the surface micromachining. Okay, as I mentioned, the commonly used sacrificial layer, again there are some numbers, but silicon dioxide is the one which I have here, that's why I showed as an example. So there are certain problems in the surface micromachining. Sometimes I have asked this question in 2 marks, 3 marks or 4 marks in examination. What are the possible problems? One is when you have 2 dissimilar materials, when you are trying to attach. So what are the 2 dissimilar materials in this example I was talking a while ago? The 2 dissimilar materials of polysilicon and the silicon attaching, or silicon dioxide and the polysilicon deposition. So there are dissimilar materials, even though they both are of the same silicon, but they are fundamentally same, but they are dissimilar materials now. So when they are attached like this, so there is a mismatch that can happen. So generally, if there are two dissimilar materials, when you try to bond, they may not stick very well always. Okay, that's the nature. So that could actually also happen. That means there will be always some adhesion problem. That means they can peel off. Some places can peel off. Yeah, you get this? What I'm saying? Or it could be sometimes like a severing along the interface shear. That means, okay, when you do lamination, you might have seen this. Imagine that when we do lamination, there could be some small air pockets and there could be some wrinkles. Yeah, have you seen that? So there could be some severing effects also can happen when you try to stick to things, when you try to do bonding. So this is an addition problem. The next one is there are 3 types of stresses can happen or when we try to stick to things. One is okay, this is the example here. So all this, as I said, the process happens in the oxidation or the CVD process. They happens at very high temperature, like 1000 degrees or 800 degrees. So in those temperatures, these 2 dissimilar materials, they will function like bimetallic strips. Do you remember the bimetallic strips when I discussed in the very beginning of these lectures? Bimetallic strips. What will happen to the bimetallic strips? Do you remember that? 2 different materials has 2 different coefficients of thermal expansion. Do you remember this? Every material in this world will have its own coefficient of thermal expansion. So when you heat them, the expansion rate could be different for different materials. So when you have 2 such bimetallic strips, so one expands faster, the one expands slower. So what will happen is, I said that one can achieve actuation in the actuator section when I was discussing about. But the same thing can be a problem now here. So when you have 2 bimetallic strips, these 2 are like bimetallic strips, 2 different materials. So when you are heating them, they will actually have some bending. Okay, it can bend because of the thermal stresses. The other stress is also, so this is during heating up. Now some cases when you're cooling the material, so after 1000 degrees centigrade, again you go to a lower temperature. So at 1000 degrees centigrade, it may look very fine. But when you cool it, there will be a bending. This we call it as residual stress. Residual stress. Okay, I can give an example analogy here. Okay, imagine that some of you might have seen some crafts that are done using the glass craft. Anybody have seen this in the Facebook or YouTube videos? They make glass craft. They heat that, and when they remove it, you can see that it bends when it cools. Yeah. So here also, when you're at that 1,000 degrees centigrade, could be fine. But whereas after the process is done, one will expect the bending of this. Again, here it's because of the different thermal coefficient expansion of two materials. So either this problem can happen even during the process itself, if it was like two materials, like two metals, or it could be even happen after the cooling as well. So this is a very huge issue in the surface micromachining process. So the first one was adhesion, that means they cannot stick well. Second one is this stress, that means there could be bending of the materials. The third one is more easier to understand, is the stiction problem. Okay, before that, how many of you, when you go to, I think these examples I might have discussed before, maybe a repetition. If it's repetition, okay, forget it. But let's see, when you go to the vegetable, do you buy vegetables? Some of you maybe. I have to buy. Yeah, so when you want to buy and you want to pick and collect your vegetables in that plastic one, is it easy to open? Why you are not able to open the plastic? What do you do for that? So if your hands are wet, then probably you can just squeeze it. You can just open it. Yeah, then it's easy. Basically, these two are plastic materials. They are stuck together. They are very bonded together. Yeah. So when you rub that, you actually produce some charges, and then you are using your electrostatic force to separate them. Yeah. Or if you make your hands wet, you are actually trying to use your adhesive force to open them, technically speaking. Yeah. So same thing here when we are trying to bond two things together, and if you imagine these dimensions are of few micrometers, very small micrometers. Even millimeter is very small. You can imagine the polythene, the plastic bags which I am talking is of millimeter adhesion actually. Imagine we are talking something in micrometers. So when you try to make three-dimensional structures to hang like this, most of the time they will just go and stick together because of van der Waals forces. Okay, because of van der Waals forces, they will try to stick, and probably will end up with stiction. We call this as stiction. So even in the overhead projector sheets, also the two sheets, if you keep each other, it's very hard to remove. What do you think is the remedy there to separate these two plastic sheets? How can we avoid that? No, that is to remove it. That's a technique to remove it. Even not to happen that, what we can do, it's actually in the overhead projector sheets, the original supplier, between the two sheets you will see a very thin paper. Yeah, so that's the spacer between the two overhead projector sheets. So that's actually now cuts this stiction or the electrostatic force between them. Okay, so same way here, while fabricating, people actually have another small sacrificial layer which is actually removed later, but this is more complicated now. So stiction is a problem that can arise because of this van der Waals forces in a surface micromachining process. Okay, the next one I was talking about, I'm talking about the micro-manufacturing process. The previous weeks it was fabrication techniques that involved what are the deposition, what are the etching, what are the such techniques. Now we are talking something on when you make a three-dimensional structure, which is mostly the MEMS devices are three-dimensional. So how are these techniques can be combined together? The first one was bulk micromachining, where I said it's only etching, just through etching, how the three-dimensional shapes are made. The second one is you add things one on the other, layer by layer, to form the three-dimensional structure, which is a surface micromachining. The surface micromachining is very well established, mostly used, but it has these problems like the adhesion. Then we have the thermal stresses, bending due to the stress which could be thermal stress while fabrication process, or residual stress that might happen after the fabrication process. And the next one is the stiction problem. So the last method is Liga process. When I was studying about this question is important question in exam. When I was doing exam, okay, that means it's important for us also. So Liga process is mainly they were trying to make this process to make high aspect ratio structures. Okay, in the high aspect ratio, when I say high aspect ratio, means that the third dimension is very large compared to the other two dimensions. So the source of this here, the idea behind is to make, suppose I want to make actually the main idea is to make metallic structures, three-dimensional metallic structures. So what they were trying to make is using the photoresist. For example, if I want to make a cubical structure, so they first make the cubical structure using a photoresist. So let's say it becomes like a hollow structure. What they do is, so making the three-dimensional structures of photoresist is easy because it's a normal lithography process. But again, using UV lithography, we have a limitation in the dimension what we can achieve. Not beyond 2 micron or 1 micron. Okay, so when you want to go for more smaller dimensions, they use X-ray as the source. This is the first difference we have in the process. We have X-ray as the source. So first the photoresist is fabricated as a mold. So photoresist is manufactured like what is made for mold? There are two mold, MOULD. Is it correct? Mold. Okay, whatever. I'm not saying the fungal mold. That is a different mold. Okay, so what happens is what they do is then they fill the mold with the material of interest. Usually it's the metals, and these metals, so metal is the main intention. Now how they fill, how they deposit through electroplating process. Okay. Electroplating is exactly how you make the ornaments which can be covered with the gold or silver, yeah, which is not inside gold but only the surface is gold. Electroplating. So they use the one of the material, the source as anode where the gold is, and another one as the cathode where you want to coat, and you put it in an electroplating solution. So the gold transfers from the source to the place where you want to coat. So similarly here, the overall steps is they do have a deep X-ray lithography. They make the desired pattern with the photoresist. They do the electroplating. So they fill the material with the electroplating, and then photoresist is easy to remove the photoresist. Then the metal mold stays, metal structure stays over it. So the steps, if you see, suppose this is the desired tube, probably they use the mask is made up of gold. They try to, so where we know that at the moment is chromium. We do an X-ray lithography and remove it. So this technique was probably, it becomes old technique probably in 2017. So probably in 2000 it was quite hot topic. But as I said, at the undergraduate level, we know the fundamentals. We can think beyond it. So, so that's the Liga process. is mainly to make the three-dimensional structure. And probably there is a combination of all this. It's a self-reading thing for you. So with this, actually, I would actually complete the MEMS part. Overall MEMS part is just this much. So if you, exam point of view, I believe all of you, I can see that all of you are having the reference text. So for the chapter 1, so if you see the overall things, how we covered. So we have the chapter 1, 2, and these two were the one actually just general MEMS thing. So definitely I can actually ask them few 1 or 2 marks questions from this. Simple things. Difference between 2D electronics and 3D electronics, such things. Then chapter 2 is more of, it says the sensors and actuators. You should not miss even any page there. Yeah, I have covered almost everything. Then we have then I went to 3. 3 was basics on materials, electrons, atoms, and things like that. After which we went to chapter 6, which had the scaling law. Then we had the 7 for materials. So 3 and 7 are like pairs. Okay. Then we have 8 for fabrication techniques. 9 is for manufacturing. So this, if we should give the reference text for the entire unit, so almost, as I said, 70 to 78% of questions I cover from this. So this is in addition to it, 1 or 2 journal articles I discussed. So those links and those papers are already I have uploaded. So you should not miss that as well. Give me an example where I use the journal articles to discuss. When I talked about chemical sensors, I used references. When I talked about biosensors, I used references. Those things you don't find here. That also should be included. But the intensity of how much to read is just exactly how much I covered. Okay. Now, when you go through the chemical sensors in this chapter 2, the information is very little. That's why I might have gone to additional references. Okay. So, overall, this is the next slide. Now, next, I would like to move on to a bit of instrumentations in nanotechnology, because all these techniques, what we saw on more applications, how do you make it, okay, principles, fundamentals. So this is common for any micro devices, that includes organic devices as well. Now, a little bit more, if you see one has to also little cover the ideas about the nanotechnology instrumentation. So this is very, very lighter. I'm just going to touch slightly, not very detailed, because this itself is a complete subject at a postgraduate level. So I just want to introduce that. There's no notes I use. So when we have the dimensions, one of the important characterization that needs at the level of nanotechnology is to view the dimensions at that level, at the nano dimensions. Okay, so the normal optical microscopes do not help us. Okay, so for example, the new microscope what we have, we can see 1 micron, or you can try to do the software zoom and see up to 300 nanometers, something like that you can see. But that's also, we are not sure. So comfortable 1 micrometers. So beyond this, beyond 100 nanometers or that level, how are we going to characterize what instrumentations, or what instruments to be used for this? So for that, that's why you are also going around this could be slightly repetition of the mechanical unit, but let's see how there's some Rama style there. Without this, the unit is not complete. So I just touch about that. So scanning electron microscope is one prime instrument to view the atomic force microscope. Then we have transmission electron microscope. So these are to view the objects or to characterize the size of materials what we try to do. So I want to discuss the principles of scanning electron microscope first. Very quickly. So scanning electron microscope, some of you have already have gone through this to see. You can basically this scanning electron microscope. So we have the substrate, we have the sample. When I say a sample, the sample consists of micron or nanostructures. They are basically built of a group of molecules or atoms. Yeah? So there are a lot of such structures, a lot of atoms. Basically, we wanted to visualize these group of atoms and image them. That's the whole idea here. So the sample is consisting of this. Usually, the sample is mounted on an XY stage, so which can move in nano steps. Okay? It's like a screw gauge. So screw gauge, what you have in the physics lab, you can move them in millimeter range. But even if you try to turn it very slowly, actually you are moving it in very small steps. So we have an XY stages. Usually they are motorized with piezoelectric motors, which can actually move in very tiny steps. So there is a stage that can actually move like that. And we have an electron source. Electron source, usually it's a tungsten, heated tungsten element, a tungsten wire. So what happens is when you apply 1000 plus volts here, this wire, it goes to very hot. We raise it to very several high temperatures. Because of that, it will start emit electrons. And this emitted electrons strikes the sample where it can strike the sample, and to guide this, there are quite a lot of magnetic lenses to focus this beam. So once this electron beam strikes, so this is a pointed spot. So once it touches the surface of these atoms, there are three kind of electromagnetic waves can arise. One is we will have something called as secondary electrons. And there could be some electrons coming up which is called as scattered electrons, backscattered electrons. Some go deeper inside and they emit X-rays. So three types of electrons arises from this substrate when the beam hits the sample. Do you know this before? No, right? Is it all of you hearing for the first time? All of you, are you sure? You have heard before? Okay. Anyway, some says no and some says no. But probably I hope I make it very clear. So when the beam hits the surface, some of them, you get a secondary electron, some goes more inside deeper, and then it gives us X-rays. Some has backscatter electrons. Now, what they do is this at certain fixed surface, they have an anode which is maintained at positive anode, right? So positive voltage, something like 300 volts. This we call it as Faraday cage. So what happens? So this is positive charge. Okay. So the electrons which have emitted. Okay. Before that, so the secondary electrons are electrons that are produced by the material. Okay. That's are produced by the material. The backscattered electrons are electrons that hit the surface and goes back. Okay. X-rays are, you know that when your electron hits a hard target, based on the material where it hits, it actually produces different electromagnetic wave, which is X-rays. X-rays, you know how it produces. So same thing. So what people do is they try to measure all the three what was reflected, or whatever the electrons which was emitted. So these electrons, the secondary electrons actually travel for longer distance. They actually have an angle. So that is actually detected by that is actually captured by an anode. Now these, then you have a CRT cathode ray tube where wherever the electrons now hits, you actually have a photodetector and an image is created. Now it's not a light, it's the way where all the electrons have hit and come back. That is captured and an image is formed. Okay? So through scanning through the secondary electrons also you make an image, or you also have the backscattered electron. You can also have an anode here to detect this. From the backscattered electron you can image or get the details of the specimen. Now with the X-rays also, one can also detect what kind of material was there. Okay, what kind of material was there? So this we call it as. Or one can also, it's each and every material based on their kind of atomic structure and all this question, probably material physics. One can actually also characterize what kind of material is there. So this is the overall principle of a scanning electron microscope. That's what we are also going through as a lab exercise. Okay, so there I think they must be showing you where is the electron gun, or how much power supply. Probably they are demonstrating you what are the steps to use, but the principle behind the machine is this: how the image is formed. Okay, that's scanning electron microscope. Any questions on this? Next is the atomic force microscope, which is quite interesting. Atomic force microscope again can be divided into many types, but we will see into three types. One is scanning probe microscope. Then we have scanning force microscope, and then scanning tunneling microscope. Okay. The last one is more interesting to me as well. Okay. Scanning probe. So the principle of this atomic force microscope. Let me start with scanning probe microscope first. So the principle is, again, when I say a sample or a substrate, it's basically a group of atoms. Okay. Now, when I say there is a material like this, so if there is a tall structure, that means there is quite a lot of atoms sitting one over the other. But if it is thin layer, means you have very small number of atoms sitting on the surface. So overall, on a big picture, the surface now looks like something like this. The surface now of this is like this. This is the surface of the material, the sample. Okay, but Usually it's actually a combination of atoms. So what happens in this case, the sample here? The first one is quite direct and simple. There's a cantilever beam. This cantilever beam, it just in a contact mode, it scans all the way. So whenever there is an up, when it hits an up, the cantilever beam has a different bending. So if this is the position, so say when it is touching here, the cantilever can have a different bending. Means it may become like this. Because of the bending here. Can you realize what I'm trying to say? Because of the different thicknesses of the surface, the beam can bend just by the contact. Yeah? Right? Do you understand this, what I'm trying to say? So, this cantilever beam is constantly monitored using a laser probe. So, you have the laser source. The light travels, hits this cantilever beam, and then there is a detector. Now what happens is in the detector, so let me zoom this, the X, Y, Z of this, X and Y. So at one point when there is very little bending, say the spot appears here. But probably when there is a more bending, so there is a spot appears here. So based on this, where this laser beam hits, and this is the photodiode here, based on this reflection of the light, you can imagine that the surface profile of this is actually can be imaged. Do you understand? Yeah? Yeah? So my intention is, somewhere I want to interrupt here also. Why this Rama is talking about these things? What is my role? Okay? What is the point of these machines are already there. These machines are used for some material science people. I feel like I'm little, you may think like this. My intention now I want to disclose. The intention is, our role of as an electronic engineers is to make these machines, to make these kind of machines for the users. We can only do this. Okay. So for example, in this case, a cantilever beam, you want to make a photodiode. The diode should detect, there is a bending of this beam. This setup is actually, who can do it? As electronic engineers, we can only construct this electronics. If you finally see who has done this machine, maybe an electronic engineer. So my whole point here is to also enlighten this and throw this light to the students. So this is a scanning probe microscope. The next one is actually, before I go to just to have some idea about, I'll talk about channeling microscope, and then I'll tell about scanning force microscope. Have you heard of quantum mechanics? There's a physics which is different from the classical mechanics, where Newton's law doesn't fit there. Okay, so the example is, if I throw a ball on this wall, we all know that the ball will come back to us because it's a rigid surface. The ball has to come back to us. But the quantum mechanics says there is some time you throw the ball in such a way it will go pass through this wall. Okay, how is this possible? So the light, according to quantum, the light behaves as a wave as well as a particle. Okay, so when I have an electrode, normally, if I say, imagine I have the multimeter tip. Okay, let's say I have a positive voltage applied somewhere. Imagine I'm bringing a multimeter tip just above this. So there is an air gap between this, between the probe and between the tip and the surface. There is a small air gap. So this air gap will behave as an electrical barrier. and it will not allow any electrons to flow through. It means there is no sufficient electric potential to have an electron to flow through between this. So there is no conductivity between this, or this is a very high impedance state. Okay. So, but what happens is, what according to quantum mechanics is, if you reduce this electrical barrier, you can have the electrons to pass through effect called as tunneling effect. The electron can pass through when you bring this very close to each other and you reduce the electronic potential barrier. I just have a small animation to show this, then I will tell you how this scanning tunneling electron microscope works through. So sometimes we don't want to study the whole quantum mechanics, we just want to understand certain things. I feel animations are important. So electron beam has wave and particle. So the barrier is thin enough, so initially it was reflecting back, so that the barrier is thin enough, the object may sometimes get through. So our sample, what I mentioned now is, whichever you are trying to do the microscopic image, they are actually a group of atoms. So the AFM tip, which is also used, is also a group of atoms. They are right, like grapes, hanging grapes. Yeah, imagine there's an edge. So the overall shape looks like the tip. Okay. So under the surface is also we have atoms. So some places we have bumps and some places we have valleys and so on the surface. Okay. So now we try to bring this tip very close to the surface. This edge is now maintained at positive voltage. Let's see what happens. So using this. So that means the animation shows that the electrons are passing through from the surface. So if you reconstruct the current intensities, okay, for every single, you can actually image every single atom. You can image in a single atom and reconstruct the whole surface. So that means when we have this, whenever there is a current flow through this, so also it depends upon how far they are. Okay, so depending on this tunneling current, so basically based on that, the current intensities, one can actually reconstruct the surface how it looks like. Okay, so this is the principle behind this scanning tunneling microscope. So it is again the same AFM setup what we have in the nano-analytical platform, but the principle now here is it's based on you bring it very close to the surface, but based on how much current it actually, it's not touching each other. It's just the last atom of this is now very close to it. How much current passes, you reconstruct the image. This is scanning tunneling microscope. Okay. The last one is scanning force microscope. Any idea what could be the principle? Any idea? I want the answers from you. How? What must be the principle? Do you remember used to draw a curve, the van der Waals forces. This is distance between two particles or two atoms. Okay, and this is the force. So when the distance is, very far, you don't have any force. Just like this, no force. There's no force between this pen and this plastic. But imagine that we go into an intermolecular space, kind of a distance. Then for certain regions of the separation between the two particles, you have an attractive force. But after certain distance between them, you have a repulsive force. Okay. Now again our A from grapes. The last grape on the one which is on the top, based on the ups and downs of this, can you imagine that the tip will go up and down? You are not touching now, but you are just going above this. Sometimes the cantilever beam will be having an attractive force, more attractive force. Sometimes it will have less attractive force. Can you imagine this? Yeah? You all agree? That's because of the van der Waals forces. So based on this, what they do, this beam, this cantilever beam, it will have its own resonant frequency. Now you should know what is resonant frequency. They vibrate in the resonant frequency. That's why they have something called a piezo actuator. This will be vibrating in this resonant frequency. Okay? Now when it comes closer and there is a bending in this resonant frequency will now get disturbed. Okay? Now they have a feedback control mechanism. Now say it was 50 Hertz to be oscillation frequency. Now because of this, when it came very close to, when the distance was smaller, this vibration frequency changed because it got bent. The beam got bent. So the resonant frequency got affected. Now we have a feedback controller such that we tune that to again to vibrate it in the original. So you know how much shift happened because of this bending. Okay. Also at the same time you also see the bending of this cantilever. So these informations are used to again make the image of the surface.
So is it initially vibrating?
Yes. It's initially you start with the resonant frequency of the vibrations. Then they set at a point, and then so this is the fundamental behind it. Now there's some reference reading materials I'll put in the Moodle, but overall the idea is this. Okay, since you're also going around the lab, I also want you to know these principles, not just like a visiting thing. So transmission electron microscope is very same, but the electron beam passes through the surface and the image based on that. So maybe since I'm not showing anything on TEM in the lab, so actually I wanted to have an AFM exercise. AFM is very wonderful. You can see even a single atom. Okay. So yeah. So I'll stop here. We'll discuss on the, maybe I want to, since I'm not fully prepared on XRD, I don't want to talk about XRD. So I'll discuss about XRD and then I'll switch over to organic electronics topics. Okay? Please tell your friends not to cut the next classes. If your friends are there, tell them. Because it really, you have to, sometimes it's easy when I explain. I hope you also believe it. Sometimes when I explain it's easy for later in the study. Okay? So tell your friends to directly come and observe.